Called Bam Bam on a Budget. You can do it. I gave this talk recently at Hardware I/O. I wasn't even planning on giving a talk, as you'll see, but this is the story of that. So it's more the story of hacking into an automotive ECU, and then we'll get into some of the technical details kind of as we go. And then any questions you have, I'll just kind of pause on each one, and I'll check the chat here real quick, and I'll see, is everything clear? So feel free to pop stuff in, and then I'll hang around at the end, and we can just go through anything that you feel like I missed or it wasn't clear when I was explaining it, or anything like that. So let's get rolling. Okay, so late last year, someone reached out to me and they said they had a job they wanted me to work on to hack into this MPC 5566 chip that's used in automotive ECUs. I didn't know who they were. I didn't know anything about them. I never met them. And after the job was done, I just wiped all communication. So this was kind of one of those, like, somebody reached out to you, is like, hey, can you break into this thing for me? And I thought it would be an interesting challenge. Now, why would somebody do that? Why would someone reach out to me? Now, everybody that's here, well, I have a YouTube channel, right? And I show all kinds of things on there about glitching microchips and breaking into things, and most of it's all smart meter related. That's where I kind of focus my efforts, just because it's a fun target to attack. But I'm interested in attacking all kinds of things, and so that's what led to this person reaching out to me. Now, when they reached out, they sent over this document, and it's written by Colin O'Flynn. It's called Bam Bam, on the reliability of electromagnetic fault injection for attacking automotive ECUs. And I kind of looked at this as like my user manual, essentially. Like, yeah, I'm going to break into this chip, but there's a manual. Like, this guy wrote a manual for how to do this. So how hard could it really be if I have a whole book? And he published videos and everything else showing how to do it. Now, the attack overall is fairly simple. So all you have, in the end, is the ECU that you're going to attack. You're going to connect to it over like a serial connection. So you're going to basically talk to it back and forth. And you're going to blast the crap out of it with EMP. Like, that's the summary of the whole attack. Like, it feels kind of deceptively simple, which is probably why I accepted this thing. Now, the way you talk to this thing, it's called a boot access module, and it's like a kind of a bootloader type of device inside the processor. So the bootloader itself, you basically send, it's got this kind of communication system. So if you're talking to it over the UART, the first thing you do is you send the password to it. So it's got a password. It can be set or it cannot be set. And so you send each character of the password, and then it echoes those characters back to you. If your password's correct, then it accepts the address you want to store your data you're going to send, and then how much data you're going to send. Then the next thing is sending all of that data. And then if all that's correct and good, it will run your code. So you can think of like the boot access module as like this little piece of code that's running inside the processor. And all it's going to do is take kind of a program you write that you send it, and if everything's good, it will execute that program. Generally, in my case, that program was to dump all the flash memory that was in the chip. But there isn't kind of a thing you enter to just extract the memory. So you have to write this program and go through this communication kind of thing. Now, if you're going to do it over the CAN bus, it's very similar. The difference is when you do it over the UART, you send one byte at a time, and it echoes one byte at a time back to you. So you get like more granular feedback, I would say, when you send your messages. That's part of the attack. That part will become kind of a little clearer later. It was a key part of how they did the timing. When you do the CAN bus, you have to send your whole message, and if your whole message is correct, then it echoes back your whole message, but using a different ID number. So the CAN, they all have this kind of like CAN ID. So you send an 11, it echoes back a 1. You send a 12, it echoes back a 2. But otherwise, the whole process is essentially the same. So what do I see? It's my fault there's a rise in car thefts. It's possible. It could be my fault that's a rise in smart meter hacking. You know, what are you going to do, right? Everybody figures this stuff out. It gets more secure if you just share it with the whole world and show kind of how insecure it is. Okay, so I should say something here that like I got a little frustrated working on this thing. And so I might say things throughout the course of this thing that is like, might seem like I'm attacking Colin. You know, let's be clear. I like Colin. Colin's a cool dude. Colin's done way more for the reverse engineering community than I've done. So anything I say is more out of the frustration of reverse engineering and less about Colin. You know, it's probably my own crap and struggle. I just wanted to put that out there because I think he's awesome, and I think everything he's done is awesome, and I literally use his tools to do this attack. So if he didn't exist, this wouldn't exist. Now, this board that I got that somebody sent me, there was nothing published about it, and I told them that I wouldn't share anything about the board that I worked on for them, what it was from, anything like that. So everything in this presentation, all the pictures you'll see are actually from a different ECU that uses the same MPC 5566 chip. The board that I got, there was only one of them available. So when I initially started, I was attacking this basically one board that if something goes wrong with it, like that's it. There's only one copy of it. Later on, I did get a second one because I needed to kind of, you know, remove the BGA chip and look at pins underneath it. And so they did give me a second board that was just dead, but that I could then remove parts and kind of figure out connections a little easier than just pure kind of guessing. Now, step one is just to identify the pins you need. So on this board, I'd kind of taken a best guess, but then when I got the second one, I popped the BGA chip off of it, just kind of heat gunned it, and I wasn't too worried about like the survival of the BGA chip because like the whole board's dead anyway. So I heat gunned the whole thing, removed that chip, and there's 4 pins you're basically looking for that are outlined in Colin's paper. Those 4 pins are the TXDA and RXDA, which are just transmit and receive to the UART. A boot config pin, this is the pin you set high or low that makes it enter this kind of BAM mode. It's brought out on these specific chips. Newer versions of this chip, later kind of families that came out, they removed like the, you know, they have like a setting where the external pin won't be, what would you call it? Like you have a way to disable this external pin so someone can't just force you into a boot mode and attack you. But these chips, that's not the case. Like you can just force them into this boot mode and try to break in. And then the reset line, so you can control resets. On the BGA chip, that's that red box that's there, where they're kind of all in this area conveniently. Now, one way I like to basically tone out kind of pins when you don't know where the heck they are is this kind of like broom method, I call it. And so you just get a bunch of copper and you spread it out. This was some, I think, like welding cable I had in the garage. But anything like coax, shielding, or something like that. And you just do the drag method across the board until you hear a tone. And then when you hear a tone, then you kind of go and you zoom in the area. So think of it as like a kind of, you know, wide way to scan it. Now, the summary here that's from Colin's paper is that the attack on this module assumes that we have external control of this boot config pin, which will force us into this boot mode. So this looks like this. So this is what it's supposed to look like when it's working. The little red characters you see there are me sending data over the UART to the ECU, and yellow is it responding, and the other yellow is just, some kind of garbage or something that it's spitting out until I send a character. So this is how it's supposed to work. Every character you send, it echoes it back. It echoes it back as long as what you're sending is correct. So I send 1 through 8 as the password. That's not correct. So then it stops echoing my characters, which you can see me sending here, the red characters. Now, the challenge I had with my board is that no matter what I sent to it, it didn't send anything back. So I would send characters, but I was never receiving anything, no matter what I did. I watched all of Colin's, videos. I'd read the paper, all this stuff. And so then I opened up what turns out to be my Bible for the next many, many days, which turn into weeks, which turn into months. And this Bible is about, 1,200 pages long, 12 or 1,300 pages. And all I did all day and night was read this reference manual, looking for anything I could find that would tell me, like, what am I missing? Why are things not working? And I was just, in it, literally all day and night. All I did was search this thing for little footnotes, something maybe that was left that I could use. Now, I did go back to my iPad history, so all the books you open, PDFs and whatnot, it sorts them, based on what time you open it. And so I thought this was interesting. So in the middle of working on this thing, like, I was seriously going through it, questioning everything kind of about my life. And turns out I was reading Man's Search for Meaning at the same time, which tells you, like, this thing was freaking really taxing me. Now, what I discovered in that reference manual is a thing called reset config. Reset config, you have to control for it to look at the boot config pin and actually do something with it. If you don't control the reset config pin, nothing will happen. So this was like, holy crap, like, I've been working on this thing trying to control this pin, and no wonder I'm not entering any kind of boot mode. No wonder nothing's responding. Now, this is where my man here kind of pissed me off a little bit, if I'm being honest. This paper, Bam Bam, as a fun fact, has 5,928 words in it. And of all those words, not a single word is reset config. And funny enough, in the reference manual, reset config is mentioned 90 different times. So, the frustrating part for me was that I'm not an academic. I'm not a PhD. I read these papers that come out. They're very interesting to me. And, what I expected, like, I guess my expectation was that these papers are meant to allow you to replicate what is in them. Like, I thought that was the point of scientific papers, is that, other people can replicate what's in them and then you build upon it, right? I don't know how you could replicate what's in this if you don't control the reset config pin. Like, it's impossible. And there's 4 different boards that, Colin shows using in this paper. And those boards, like, you would have had to control the reset config pin on them. Like, so how this got missed, how it didn't end up in the paper, how it didn't get caught, like, during any kind of review or anything, like, is kind of, like, mind-blowing to me. But it's possible it just wasn't caught. I mean, my kind of mind went to, like, oh, I bet, the companies told him not to include certain details. But most people I talked to were just like, no, man, it just got missed. Like, that's probably what happened. Now, there's kind of some more bad news. So I discover this reset config thing. I get it set. I set the boot config, all of that. But no matter what I do, the transmit line that's coming from this chip just sits at 1 volt. It does not, like, I don't see anything coming from it. No matter what I do, like, I'm sure at this point, like, all my modes are set, everything's right. I don't have any other boards to verify it against, but I mean, I've literally been reading the spec sheet for like days and days at this point. Like, I know it's right. There's something doesn't feel right. Like, why is the transmit pin just sitting like that? Now, I'm not sure, like, if the receive line is still working. So, like, I'm sending data to it. I'm trying like a zillion different baud rates, like just trying to figure out what's going on. But I'm getting no response. Like, that echo you saw with those yellow characters is not coming back for me. So, a bit of an update. I literally quoted 5 days to complete this job. In retrospect, uh, that's probably psychotic, because I had never done a ton of the stuff that's in this. So to think that I'm going to get this board that I've never seen before and perform this attack that I've never done before using some tools that I've never used before, and some tools that I don't even have in 5 days, is kind of ludicrous. So at this point, I'm 10 days into the 5-day job, and I discovered the UART's dead. The UART is my exfiltration point to get my data out. So I'm like screwed at this point. Like, I can't, how am I even going to get the data out? And I'm already double the amount of time that I've quoted to do this freaking job, right? But Colin, in his paper, he does talk about the CAN bus quite a bit, CAN versus UART. And he talks about, like, okay, maybe you could use the CAN bus. He never says he's tried the CAN bus. He never says the CAN bus will actually work. He just says, like, okay, the CAN bus is another way. So I start to think, like, oh man, maybe Colin's my savior after all. And he's come to me with a new method that I can try, considering the UART on the board that I'm trying to extract this data from is dead. So it's kind of like what to do at this point. I don't want to use the CAN bus. Like, if I'm being honest, like, I don't want to come up with some whole new attack that's completely undocumented. Like, I'm just trying to do this job and get paid, like, I could use some cash. So I reach out and I just say, hey, do you have another board? And so I'm waiting to hear back to kind of see, like, is there another board? Can I just, test another one of these? And I realized, like, oh, I don't actually know anything about EMPing a board. Like, I have this Pico EMP, but I've kind of, like, never really done anything with it. So I should probably spend some time learning about that. But there's something that is like a main point, that I think I should bring up here, which is, like, when you read Colin's paper, it's very specific. Like, one, he's using a chip shouter. That device is like $4,000. I'm using a Pico EMP, which is $50. So there's a, like an order of magnitude difference in the product that I'm using to attack this. He's very specific. He uses 444 volts to pulse this thing. So I don't know anything other than 444 volts is stuck in my head. Now, why does that matter? It's because the Pico EMP only goes up to 250 volts, and the chip shouter goes up to 500 volts. So, I'm not completely convinced that if I buy a chip shouter, it'll work. But I'm also not sure that if I use the Pico EMP, it'll work. But, I kind of start to think, and I'm like, well, if you're going to spend all the time and effort to write one of these papers, like, it's a lot of work, and attack all these boards and get this stuff, like, if you're Colin, would you try to sell your $4,000 device, or would you try to sell your $50 device? And I'm like, he's a smart dude. He's a businessman. It's like, might as well, make sure that the range of what you're using is for the high-end device. Now, this here is a very good summary of what I had done up until I kind of took on this job with a Pico EMP. I would just point it at stuff. I would press the little button and I would see stuff reboot. I'm like, oh man, look at that. I'm freaking EMPing the crap out of this thing. Which is not the controlled kind of setup that I need to actually cause a fault, which will allow me access to extract memory. So I'm not even sure, like, how do I send an external trigger? Because I have to control this from like a chip whisperer or something else that is going to watch all the signals on the main board and then determine when to, send the glitch and then send that signal to the Pico EMP so that it can pulse the chip. How do I even control like the width of the pulse or the voltage of the pulse? Like, I've never done anything with it. All I've done is literally press this button and move it around. Now, this is kind of good to look at these two setups. So on the left here is a setup that is what you would kind of use in these environments. It's like an XYZ table. You see it's very precise how it's moving around on the chip. I mean, you're going to scan like, the silicon die that's inside there. Obviously, the features are very small. That one on the left can move at like micrometer, scale right across the thing. Let's contrast that with what I'm using on the right, which is essentially a magnetic clamp that a machinist would use to hold like a gauge against, something on a lathe to measure run out or whatever. And I have my Pico EMP clamped in it, and I'm just kind of scooting the thing around looking for the right spot. So, equipment wise, vastly different. So let me check the questions here real quick, make sure I'm not missing something you guys are asking. How does one charge money for this? You guess I guessed a fixed amount and I quoted it. Probably not the best way to do it, but if you charge hourly, like someone would feel like they're getting scammed, right? Like, I'm like, well, I'll just charge it by the hour and I'll work on it for 6 months. But if you do quote a price, the risk is if you don't know what the hell you're doing, like I kept working on it until I figured it out. Maybe other people wouldn't do that, So yeah, so it can be kind of tough to quote. Yeah, 4K is a lot for a chip shouter. I mean, but considering how much time I spent, not sure. Maybe the 4K wasn't that much, honestly. Time gets eaten up pretty quick, Let's see. Yes, this is a E39A board. There's E39 and E39A. The one on the right is E39A. We'll get into why that matters here in a moment. So this was something interesting I discovered that I felt was like, I probably didn't expand on this enough during my Hardware I/O talk, but I am going to expand on it a bit here. So let's look at this thing real quick again. The one on the left, the way you generally profile how to find like a glitch using an EMP thing is you would take the chip, probably on a development board like what you see there on the left, you would write some code. So the code would be like a loop that's running. And the loop is just like a forever loop. So while one, increment a counter or do something. And so the loop should never escape. But if the loop does escape for some reason, then you would print out something else and maybe go back to your main loop. What you then do with the fault injection setup is you start inserting faults and you scan all across the chip and you see, where do I cause that main loop to break out? Which should never happen because it's just a forever while true kind of loop. You then have kind of these points you determine where the chip is vulnerable. You try different voltages, and so you profile the chip basically, and you find where can I attack it to cause a fault. I didn't have that, right? Like I had the one board the dude gave me with the code that's running on it that needs to come out. So I can't do any of this profiling. So what I discovered was purely by accident, like it's not some super genius move. Probably the genius was, or the smart thing I did was watching the oscilloscope and thinking like, oh, that's interesting. Maybe I could use that somehow. but this wasn't some pre kind of genius thing. So what it is there's a pin on the chip called clock out. And all clock out does is take whatever clock the chip is running at and it spits it out. And when you glitch the chip, what I would see is that that clock would actually change a bit. It would kind of stutter and it would change frequency from like 12 megahertz to 16 and then back down. And if I glitched it too hard, the clock would actually just drop out. The line would go low. Now, I discovered this because what I was trying to do was synchronize my chip whisperer. So the chip whisperer is what's, basically watching everything that's going to go on, coordinate the sending of messages and all these things, glitch the chip, and then, watch the output. And so ideally you synchronize like the chip whisperer with the clock that's running on the board. So every time you hit it, it's some certain clock cycle. It's like exacting because those things are both synchronized together. So my idea was I'll take this clock out, I'll feed it into the chip whisperer, and I'll use that as my clock, and then I know everything's synchronized. When I tried to do that, the chip whisperer was just freaking out all the time. And so I started looking at this clock out on the oscilloscope, and then what I noticed was like, oh man, it's falling out, or it's doing these weird things. But then I put the Pico EMP into a mode where I'm just kind of sending pulses. And so I would just move that little thing across the board. And when I would see this clock output start to freak out or go to reset, I knew, okay, I'm in the right spot and maybe I need to adjust my settings. And if I adjust my settings just to cause the clock to kind of stutter a bit like it's doing here versus completely fall out, I'm in the right spot. So I don't need to write any code. I don't need to make that loop to scan the chip or anything else. I can just use pure hardware to look at this. A lot of chips have clock outputs like this. So it's a very good way, like a no code kind of way to just watch this thing on an oscilloscope, move your probe around, and when you get in the right spot, you basically got a complete indicator right there. All right, how does one learn how to work on electrical boards? You just do it. Like, I spent like a long time. Just the way you learn is be comfortable being incredibly frustrated and thinking you don't know what you're doing and thinking this is complete crap and you'll never figure it out, and then just don't stop ever. And if you do that, you just like you'll become good at anything. Because all you'll do is spend all day and night trying to focus on how to figure this thing out that you've determined you want to figure out. For me, that's it. Like, that's how I do it. Other people, maybe you go to school, you go to a class, whatever. I'm not sure. But for me, it's just like work on it and obsess over it and do not let it go until you figure it out. Okay. But in the back of my mind, like, is this 444 volts? Like, okay, I'm doing this. I'm causing these faults. But like, is it enough? I don't know. I've never done it before. And all that I can think about is like, is it enough? I even did so much as like, I went on to DigiKey and I ordered parts to try to convert my Pico EMP to 500 volts. So I have, kind of these parts sitting on the side that like, if I get stuck, here's a MOSFET that's rated higher, here's a capacitor that's rated higher, some diodes, kind of the parts of the circuit, because the Pico EMP is open source. So you can see all the schematic. So I was like, okay, if I shift these parts around and kludge something together, if I need to, I can get to 500 volts. Now, the other thing that's important in this setup is the coils. So when you're doing like voltage glitching, all you're doing is, basically controlling the voltage that goes to the chip. So you're dropping it down or whatever. When you're doing EMP glitching, you have like many more variables, right? You have the variable of like, where is it on the chip? You have the variable of how big is the coil, how many turns is the coil wound clockwise or counterclockwise? That is the one thing that definitely I've seen make a difference. But one of the cool things about going to Hardware I/O was I met a guy named Cristofaro, I've tweeted some stuff recently of talks he's done. This guy is like the uber genius of EMP glitching, and any paper, anything he puts out, that's what you should look at. It's like, if you want to do this, like my stuff, I think is like, it's cool to maybe get you interested, right? You're like, oh, that looks interesting. I'm not a definitive source. Like, this is kind of like what worked for me. His stuff is like what I go read now. I talked to that guy for 30 minutes. I feel like I advanced my knowledge by like an entire year. So that's a cool reason, if you're thinking about going to these conferences, like, it's definitely worth it to chat with people, because you can learn a lot. Here what you see is I have some different size ferrites. This is just basically ferrite rods that are on the left there that I'm winding that wire around. The size of it is just kind of going to control the size of your pulse. I ended up going with like a 3 mm, and it's the only one I tested. So smaller might have worked, larger might have worked. I don't know. I wound only like 4 coils around it because my kind of thought was like, my voltage isn't as high. So if my voltage isn't as high, I just want to try to not have a coil with so many windings, because you might need a higher voltage for that. And one thing that I did notice is, because my setup is all kind of lower voltage, lower power compared to a chip shouter, getting that coil as close to the processor as possible does make a difference. And we'll see kind of like the silicon in the package of the chip is also down a little bit. So, you're working with distance, and things are falling off at it's exponential, right? So the square, the square root or whatever of the thing is how stuff is falling off that pulse. So you're losing energy really fast as your distance increases. Now, so I just sanded, that's like a granite surface plate that's down there, but even a piece of glass with some sandpaper on it, you sand that coil and get it as close as possible. Now, one thing that I realized is I needed to control the voltage of this thing. Like, I need some variables. So location is a variable, and technically you could kind of think as like the z-axis. Like, even if I didn't change the voltage, if I just moved it up a little bit, that is also kind of probably the same effect. It might not be, because it's like, how is this pulse coming out? But it might be. But I don't have fine z control. Like, you saw my setup. Like, there's nothing precise about that setup. So my plan was just plant the thing right on top of the chip. So my z control is, I'm just sitting on the chip, and then I'm just x and y are my variables, and maybe I can adjust the voltage somehow. So there's a little cover normally on the where is it? Let's see if I can show you this. There you go. There's a little cover normally on the chip shout, or the Pico EMP here. This little red cover, and it says don't remove because there's high voltage. So the first thing I did is I removed that, and that's what's underneath it right there. And it has a little header to plug in, and so you see I'm reading 250 volts from this thing. Now, the cool thing about the Pico EMP is it does have like this kind of whole serial style interface. So there's a USB port on it, and you can actually control stuff that's there. And one of them lets you set the pulse power and the pulse time. The pulse time didn't seem to matter at all, but the power was what I was interested in. But it's set in this freaking really weird way of like, I think you're defining like the pulse width modulation value in some sense. So what I did was I would send these different values like 0.05. So the first value in that table says 50, 0.05. I would send 0.05, and I would measure on the voltmeter what voltage am I getting. And then I would send, another value and what voltage and what voltage. So I built this little table that's like a conversion table. Then what I did was I found someone's interpolation code they had written that basically, if you feed in a little table of values, it will interpolate all the other values for you. So then instead of sending these weird, kind of whatever pulse width modulation values, I can just say, I want to do a pulse voltage of 100, and this whole thing will interpolate it and whatever and put it across. This is already on a GitHub, so don't worry about the code that's here. All of it's posted on GitHub. You can see it. But this is super handy if you're going to do anything with a Pico EMP. This just makes the usage of it in a more kind of yeah, in a better kind of controlled type of attack you want to do versus just the little button press and stuff like that. I'll take a look at comments real quick, see if I'm missing anything. Be okay to break crap, 100%. You're going to break a lot of crap if you work on hardware. So if you want to hack things, don't hack things you can't afford to buy like 10 of, because you'll buy, easily 10 of them or whatever, especially as you're getting started. It's an accurate description on how to learn how to do this, that's for sure. Slap it on a 3D printer. That's what most people do. They put these little, like a Pico EMP on a 3D printer. I might do that because it would be fun to run some tests of scanning. So after I talked to Cristofaro, he said something, that kind of blew my mind. Like I was worried about coils and, well, what coil do you use for this and what coil for that? And he's like, I use the freaking same coil for everything. And he's attacking crazy stuff like arm trust zone kind of things and stuff like that. And I was like, the same coil? And he's like, yep, one coil. And he doesn't even play with the z-axis. Like he scans it around because, what he said is like, if you're scanning around a chip, where you're actually causing the fault might not be where you think you're causing the fault. So I might be like, well, you need to place the probe right here, over the letter M on the chip. The fault might actually be somewhere over to the side. And maybe the main energy that's focused there, as it's going out, it's decreasing, right? And so it might be that over here is where the fault really is. And so if you scan the chip, you can kind of see, like, as I move around this area, maybe the fault is kind of in the middle of where I'm moving around. And so some amount of that energy is causing something there. And it was kind of really eye-opening to me because I was just paying attention probably to a lot of things that weren't going to be the things that mattered. So yeah, I think probably doing like an XY table with a cheapy little 3D printer or something is probably an interesting next thing to do if I was going to attack more stuff. Although, I mean, once you're able to find the spot and whatever, it's surprisingly easy using that crappy little setup that I got or whatever. Okay, so this is just a little video that kind of summarizes that stuff. So you see I have it hooked up here. It's basically reading 250 volts. This is the pulse width modulation that is going inside there. So inside the Pico EMP, to charge the capacitor, there's this little PWM thing that is running that charges the capacitor to a different value. So this is like, I think 10 microseconds per division. And you saw it was probably like an 8 microsecond pulse that it's off. But then as I adjust that pulse, we see the voltage changes. So now I can set it to about 50 volts, and the pulse is a different width. And I'll go over to the computer here. I'll type in another little voltage value here on the screen. So I was doing 50 there. And the width of the pulse is probably the off time, would be my guess, which is why it got longer. And then, the voltage went down. And so I set it to 100. It's within like plus or minus, a volt or two. So, it's pretty darn accurate for being as kind of, lo-fi as it is. Each board you might have to profile separately. But, in the back of my head, right? Like, okay, 250 volts, voltage control, all this crap, but is it going to be enough? Like, is all this for nothing? That number just tortured the hell out of me. So I get a message back from the mystery person, and they say that's the only board I have. And so I'm like, crap, you know. And I'm thinking crap because, like, was this dead when I got it? Did I do something that caused it to die? Like, I don't know. I don't have any way of knowing. All I know is that the UART isn't working. So because there's that uncertainty in my mind, I don't just default to, well, I'm going to send it back. Like, say I had gotten this board and the UART was dead right away, and this test was simple. I'd be like, well, hey, man, you got to send me a board with the UART that works, or the price is going up because I got to build this whole attack. But I don't know. I don't know if I did something that caused the UART to die. I don't think I did, but I can't be sure. So I'd been reading about the CAN bus quite a bit over time, and so I thought, okay, maybe I can do it. Now, I thought maybe I could do it because I've never done anything with the CAN bus. So I had that great sense of like when you're completely ignorant about something and you're like, I could probably do this. How hard could it really be? It turns out it's pretty hard. But I had that sense in the beginning. Now, if we look at the CAN bus, to me, it's like I looked at it, I was like, well, it's kind of just like a UART, right? Like it's just, it's a different kind of way of sending data. But as I was working on it, I would send messages. So this is kind of, you're looking at the oscilloscope view of stuff going across, and then the CAN tools on Linux kind of view of stuff. And I would try to glitch it. I would send my CAN password, and then the whole bus would freaking flood with data. And just stuff's coming across. I'm thinking like, oh man, this is awesome. Like I glitched this thing and it's just dumping out all kinds of stuff. Maybe that's firmware that's flying across. Like I'm not sure yet. I gotta really take a look at it. But what I kind of started to realize is like, is this really coming from the processor, or is my tooling, doing something weird? And so I started to become less and less confident that this is the processor dumping data over the CAN bus, and more like maybe my tooling is having some kind of issue. So this is how I was sending the data. So if you're familiar with CAN bus, what I was doing is I had these messages defined. So the first message up there, it's a feed face cafe beef, is kind of like the standard password for this thing if there is no password. So I was sending a public password. I then had a message that is the data where it's going to get loaded, and I would use this bus.send, which is what you see at the bottom there, to send that message. And all I want to do is send one message, right? But sending that one message completely floods the bus. Now, that's because if we take a very close look at this, when you send one message on the CAN bus controller has a really awesome feature. That feature is that if it doesn't see this little tiny dip at the end, which is called an ACK, it will just flood the frickin' bus like crazy until someone responds to the message. So it sends a message. If it doesn't hear a response, it's just going to go buck wild until it gets a frickin' response from whatever's there. And so this is terrible if you're trying to glitch something, because you're literally causing faults in the chip. So of course it's not going to respond to these messages. Now, and not all the time at least, right? Now on the UART, what was different on the UART is you would send 1 byte and then you would get a 1 byte echo. And so you could just send the 1 byte and then glitch after the 1 byte. And with a UART, when you send 1 byte, that's all that gets sent. Not so with the CAN bus. So I kind of took a break, and I thought, maybe the freaking CAN bus isn't going to work. Maybe I should look at JTAG. JTAG, the challenge is you have to get a separate programmer. So you can't just use like OpenOCD and a standard JTAG interface for these MPC chips. You need this thing made by PE Micro. It costs money. You need software made by PE Micro. It costs money. So you have to kind of invest in this setup, which I did. The thing I got on eBay, but the software I just had to buy from the company. And why I did it was because reading that kind of forever reference manual, I saw this chip configuration register and this thing called a DisNex bit, which is for Disable Nexus. Nexus is the thing you connect to essentially that gives you JTAG access. So there's hundreds of these registers that get set when the chip boots up. My thought was, maybe I can hit this register, like somehow, right? Like It's kind of wild to think about. Like, I don't have any idea when this thing's getting loaded, where is it getting loaded, whatever. But I basically decide, what if I turn on the chip and I just try glitching all along over time and see if I can get myself JTAG access. Like, a lot of people do this to get JTAG access. And I freaking got JTAG access. Like, that's wild. I used 250 volts. The probe was placed right there. I have JTAG hooked up, and I managed to get JTAG access on this thing. So, I mean, like, my heart freaking dropped. I was like, first of all, I was like, thank God I'm done with this goddamn project. And so I'm looking at the screen, and it's almost like a bit of disbelief. And so I go to read the flash memory, and when I do, all I get are zeros. Nothing comes out of it. And I realized, looking at the manual a bit more, that yeah, I had managed to get JTAG access, but the flash memory wasn't unlocked. And so perhaps I could find a secondary fault, like to get in and then to glitch again to get flash access. But I was like, I don't know. I mean, like some kind of double fault setup. Like, I don't know if I got that in me to figure that out. But I would say on this, one plus side is um, I did manage to do it without 444 volts. I didn't actually get access to what I want, but I did cause the chip to do something with a pulse that's below 444 volts. Now, so the whole time I'm working on the JTAG, the whole time I'm doing everything, I'm still like reading everything I can find because I don't know what attack vector might work. The only thing I know is the UART's dead. I can't use the UART, but I'm still reading about the CAN bus. And so I'm reading a data sheet for a CAN controller chip, and I see this thing called one-shot mode. And so one-shot mode is basically kind of what it sounds like. You can put the controller into this mode, you tell it to send one message, and it doesn't care whether there's an ACK or not. It just sends one message. And I'm like, that's exactly what I need to glitch this freaking thing, right? So I'm looking at it, but the little cheapy kind of USB CAN controller that I bought off of Amazon doesn't support this mode. I'm looking, I'm using all the tools, the Linux CAN tools. I'm trying to do it, and there's not a mode I can set. So I'm like, I know it exists, but this controller won't let me do it. So I end up in this kind of build versus buy scenario, I would call it. And I didn't want to actually build anything, right? Like, I would have just bought a tool, but the challenge was the tools were kind of expensive. I didn't know how long it would take to get to me. This tool supposedly does support one-shot mode, but the only way I could figure that out was I was on I was searching, and I see a forum post where a guy posts like, "Hey, did something happen? The latest update? I can't do one shot anymore." And they go, "Oh yeah, push this other update." And then I got to use some unknown software they provide to talk to the thing. So it's kind of feeling like, man, I'm going to do a lot of work even if I buy this tool, and I'm not even 100% sure that like it's going to work. Or I can just get an Arduino from freaking Micro Center down the road. Cheapy, 13 bucks, a $7 hat. That $7 hat is using the exact chip from the data sheet I was reading. So it's like, I know that supports one shot. I'll just have to write some code or whatever to actually make it do that. So that's what I did. It only ended up taking maybe a day or two. Most of it was figuring out like how to load all the CAN kind of register stuff in that chip. But what I did was just make an incredibly simple thing where I just used two pins on the Arduino. And if I hit one pin, it sends a password message. If I hit another pin, it sends the address and the size of data that's going to come across. And so those are just hard coded in it. That could probably be like improved to be like a serial interface where the chip whisperer could kind of send these commands to it. But for what I needed to do, it didn't need to be like, I just needed this. And so this is also on GitHub. This is, for 20 bucks, a super handy tool if you need to do one shot kind of stuff. Okay, but I shouldn't discount like the emotional roller coaster that this was. So, it really is kind of like screaming into the void. I found myself walking around my neighborhood just frickin' staring at birds and trees and wondering, like, what am I doing with my life? And what the hell's going on? And that's the reverse engineering process for me. It's probably different for everybody. But one of these days, I was walking around and I was listening to David Goggins, which you see in the top right there. And he's not so much a motivational speaker as he's got a certain kind of message. And that message resonated with me quite a bit. And that's the reality. Like I was kind of like, I'm coming up with all these excuses and reasons and should I still be doing this and all this stuff. And it really boils down to like, you just got to frickin' make a decision and do it. And so on that walk, I just decided I don't care how long this takes me. I don't care if it's months or years. Like I'm not stopping until I figure this out. And if I don't ever figure it out again, like if I don't ever figure it out, I'm just disappearing. Like there's no more Richessum, there's no more nothing. That's it. Like it's work on this or die. Like there's no turning back. And basically making that decision, 2 days later I figured it out. And so it's amazing to me like how at least my mind, like how your mind is always looking for escapes, you know? Like how can I get out of this thing? What can I do to alleviate the pain? Please make it stop. And you have to just fight through it. And when you make the decision, like that decision of like it's this or never, it's amazing like how like the mode my brain shifted into. Now obviously I'd been working a lot along the way, but that really did it for me. So here, what I'll explain a bit about the CAN bus and what the challenge was. But I'm curious in the chat, you guys guess what do you think the voltage was that actually did this thing? Keeping in mind that I purchased the stuff from DigiKey to go to a higher voltage and all these things. So after all was said and done, what do you think the voltage was that it took to glitch the CAN bus? And while I'm waiting for that, what I'll say is that the uh, arbitration and matching timing. So the challenge with the CAN bus is with the UART, it's very specific. Like when you send a byte of data to the processor, that byte of data like gets sent right over and then it's processed. And so it's very deterministic, the timing of when to glitch. Like you send the last character of the password, you glitch in the same spot, and then you start sending the next stuff. With the CAN bus, there's this window of time because there's like a separate engine running on this processor that's receiving these CAN messages. And then they go into a buffer and then they're sitting in this arbitration time and then it gets sent to the processor. So it's not like you hit the same spot every time when you do a CAN attack. It's like you're doing the CAN attack, the message stops at the same place every time, but you're kind of attacking in this window and it's almost like statistically over some number of hits, you'll get to it. And so for me, it takes about 10 to 15 minutes and it's repeatable. So every 10 to 15 minutes, I can glitch it and it gets in over the CAN bus. Now here we go. We got a zillion guesses, so I'm going to read them. 180 volts, 250, 128. So I'm going to guess 444. That's a freaking good guess considering how many times I put 444 in this presentation. 75, 48 volts, 5 volts. That's super low. I don't think I can go below 50. 24, High. Yeah, Pi was a great movie. Pi's a freaking, that's that black and white movie that was playing in the bottom right. It's called Pi, like the symbol pi. That's worth watching. 60 volts. Freaking 60 volts was all it took. Like after all the stressing and agonizing over this, it was only 60 volts to freaking glitch this thing. And that's also dependent on the size of the coil, the number of the windings, all these kinds of things. But you know, it wasn't the freaking 444 that it plagued me. It wasn't even 250. I ended up lowering it way down because I kept like, it just kept not responding to anything. And so I thought, well, maybe it's too high. Like it didn't seem right to me. Like I was pegged at 250 for all my tests, which is the same with the JTAG you saw me do. But as I lowered it more and more, I started getting better and better results. And then it's 60 volts, like my loop just runs 60. And when it gets to 61, it goes right back to 60. Yeah, at 60, it was super, super repeatable. Obviously, for me, that's everything related to my setup and how it was. But it definitely wasn't a high voltage. Now, but in the back of my mind, all I've done is basically get it to respond to the second message. So at this point, I send the password, I then glitch it, I send the second message, which is the address and the amount of data. And if it responds to that message, it basically means I found a glitch that's allowing me to get into that boot module. But that's all. Like, there's no firmware, nothing's coming because of this. So in the back of my head is that freaking JTAG experiment, right? Where I did get in, but then I read zeros out of the flash. So still, I'm not like super confident that I've got something. I'm happy that I did manage to get this CAN bus thing working, but you know, it's I'm not popping bottles at this point. Let's put it that way. Now this is what's in Colin's paper. That they had to basically create a second stage bootloader to validate access, which is like reading the shadow memory, which is this part in that chip, you know, extracting all the flash and everything else. Now, Colin doesn't share this second stage bootloader. I'm not sure why they didn't post that. I guess technically you don't need to for that paper, you know, to kind of like for you to test the premise of that paper, which is glitching and seeing it respond to the second message. But it'd be freaking nice, you know, like for anyone else that wants to do an attack like this. It's not top secret information. And it's, I'll tell you what, it's freaking damn hard to do. And so yeah, so even though I had this access, I still had a freaking road ahead of me. And the challenge was the road ahead of me I could not solve with just the one board that I have. I need a development board. Because like how could I code up an entire second stage bootloader using the only board with the only information I need to extract, and the only way to load the code would be to like glitch it for 15 minutes and then try to put on my code that I'm writing. Like I'm not like a mega software developer. So like I'm an iterative software developer. Like I'm like, does it work? Run. Does it work? Run. Does it work? Run. And so I need you know, some kind of development board. But these freaking development boards for these things are expensive as hell. Like it's almost $2,000 for this MPC development board. And I'm like, dude, I'm already losing my ass here on the quoted amount for the job. So I'm not dropping $2,000 on a development board that's going to sit in a bin with the other development boards when I'm done with it. But I'm also reading all kinds of car hacking forums the entire time I'm doing this. And I'm scanning for anything. I mean, I'm looking for knowledge from anywhere. I don't care where it comes from. Like anything that might give me a hint on what to do, how to do it, whatever. And so what I see is that there's these other GM ECUs that are friggin' dirt cheap, like $30, you know, on the left hand side, which are the E39As. I mean, they're basically giving those away. You can't even get like Starbucks for that price. Or the E39 itself, which is $64.95 on the right. Now, the difference between these two is that the E39 has on it, when you look at the board, an MPC 5566. These E39As, most of them have this SGM PPC whatever chip. Both made by the same manufacturer, but I'm like, is that the same chip? You know, like if I build an attack for this SGM PPC thing, like, would it even work? But I came across some posts on these forums, and people were speculating that this SGM PPC chip really just is an MPC 5566. No one had confirmed it or whatever, but they kind of like, I can access it the same way and everything. And so I thought, okay, like, I'll just give it a go. So I bought all of them. Like I bought, all the E39As you saw there and the E39. I thought like, this is cheap enough. Like, and I'm going to have to destroy one or two anyways to figure out what I need to figure out. But it turns out like some of these tuning boards, they actually give you a lot of the information you need because they sell tuning tools to connect into these. So there's pictures of the lids popped. You can look at the circuit board. They show you where the CAN bus connections are, where you need to apply power. They show you where the boot pins are that you need to set to put it into boot mode. So it's like, as far as building a development board goes, like, this is pretty freaking sweet. I kind of have the information I need to connect it up and put it into this bootloader mode. I know where to connect all the CAN bus pins, so I don't even need to do the drag method of the wire across the board or anything. It's kind of like, here's everything I need to know to turn this thing into a development board. So the first thing I did when I got one of these E39As is I was like, well, I have fuming nitric acid, right? I made this as part of my talk last year at Hardware I/O, and you can use fuming nitric acid to decap microchips. So I thought, like, how about we just settle the debate, right? Is this this SGM chip? What is it? So I put some acid on there. I ate through the top and everything. I threw it under the microscope, and sure enough, right on the bottom right of that chip there is MPC 5566. So I was like, sweet. This is probably just some custom labeling for GM. Maybe it's a, something they did to just say, okay, this is GM specific part. Maybe they don't rev the silicon. Who knows? But they created this specific part number for them to use on their board. But it's just basically an MPC 5566. So then I had some comfort. I'm like, okay, I can really try working on these boards and building attacks on them and writing my code, and know that it's going to work across to the other boards. Now I ended up with a bit of a problem, and that problem is that these boards are locked. Like, they have a password on them, and so I can't actually access it over the CAN bus to write my code, even though I have a glitch right now that will basically allow me to, get past the password and send the next part. I need to basically write this secondary bootloader. It's going to take me hundreds, probably at least high tens, maybe low hundreds of iterations of compiling and running. Just that's what I'm thinking in my head to actually get this to work. And so I can't be on a 15-minute load cycle every time, and be not sure. So like, I need the password for this thing in order to just expedite the development process. So on one of the forums I was on, I remember seeing this post. And this post was, this guy had figured out, if you send him a picture, so like this picture I have here is the picture from my board. If you send him that picture, he can take those numbers, and he's got some algorithm or something he runs, he can turn it into the code that gets you access. And it appeared, from my kind of looking, that he was based out of Russia. And so I was like, how can I track this person down and see if they'll do this for me? They seem pretty open in this forum to doing it. So these are my messages. I went on Telegram and I found him. I reached out to him. And I said, hey, I'm trying to do this on an E39A. I had been, trying to use a PE microprogrammer. Would you be able to calculate this code for me? I'm trying to appeal to the technical side of this person, because I read like every single forum post they had ever posted, and I could see, they're very technically oriented and minded. So like, will they, give me the homie hookup on this thing? And so, boom, immediately, I'll calculate the password for money, $50 crypto. And I'm like, damn, like, geopolitically, do I send $50 to Russia? Is that a problem even? It kind of like, I kind of just hate paying for stuff like this, honestly, because it's like, you never really know, even, are you going to get something or not? And so I thought, like, well, I'm still not convinced though that like I've done a good enough job. So I go, hey, let me give this person something of value. So I said, hey, I noticed on these message boards, everyone was speculating about this chip. But I actually decapped it and I determined that it's an MPC 5566. And I just thought, like, you're the kind of person that would want to know this information. And so, boom, says, I'll calculate it for you for free. I was like, sweet. I send the picture. They send me the code. That is the actual code that I used to access mine. And then after that, started chatting a ton about hacking all other kind of ECUs. And I was like, oh my God, I'm going to get freaking sucked into this ECU hacking world. This is what Colin talked about. Colin published some of this stuff, Colin O'Flynn. And then, like, if you look at any of his web pages now, he's like, if you're a tuner, do not talk to me. Because I think the entire tuning world was like, descended upon Colin to, get more information. And so this guy was very interesting. He's working on all kinds of crazy stuff, but I was like, I'm just trying to do this thing, and I really appreciate you hooking me up. So I'm not going to go through all the code here. This is Code Warrior that's actually used to write this secondary bootloader. But what I'll tell you about is kind of the things that were very, kind of like hurdles that I went through. And so the first program is like a hello world for an embedded devices. I just wanted to cause a pin to go high and low, blink an LED basically. So I'm watching it on the oscilloscope. That was incredibly hard. Because when you build this bootloader kind of code, it doesn't run the same way standard code would run that would compile and get loaded into Flash. It gets loaded into some segment of RAM and then told to jump there and execute. So it has to initialize all kinds of stuff on its own. And so even the files that are there, you have to add extra files into the link order, all this kind of stuff to get this to actually work. This is the link order right here. You had to put like this start file at the very beginning of the link order. You had to tweak all kinds of stuff with the frickin' the definition file. You have to define all your memory segments, where you want to put things, the length of those segments, all kinds of crap to get it to work, just to get that frickin' blinking light test code to work. Once I got that to work, then it was kind of like, okay, can I send a CAN message? That's its own set of crap you have to do. The board initializes at like a 400 kilobit CAN rate, but all the sample code is for like 500 kilobit. So you have to calculate a bunch of crap of how to, like, these CAN messages, what's this segment length and that segment length and all this other stuff. But then I was able to transmit a CAN message back to myself. Then I tried to read some of the flash memory and send that over the CAN bus, which was, I was just going to read the password section because I know what the password is. I'm using it to access it. If I can read that section from flash and the same password comes back, then I know I've actually figured that part out. I got that, which was good news. And then I have to read the entire flash from the chip and dump that out. And so these are the kind of programs. You'll see that on my GitHub. All of this is there. All of these sample programs are there. So if you want to try, running any of this stuff, doing things with it, like, you have all the code and all the pain that it took to figure it out. Now, one of the big hurdles was this chip uses it has like some error correcting ECC thing going on with the memory. So basically, if you don't initialize all of the memory that the chip's going to use, so like the code you're sending, any stack space, anything else, this block of memory, it will fail an ECC check of its own memory, and it just never runs. So for the longest time, I was like, I'm sending code there that probably should have run, and nothing was happening. It's because I wasn't initializing like the RAM space, the stack space, the full kind of code block that this thing's going to make use of. And so the way I ended up doing that was I guess I couldn't figure out how to do it easily inside of my code itself. So basically, to have the chip, when it starts from its kind of bootloader spot, initialize all of its own internal memory that it was going to use. So I thought, like, well, I don't really need to do that. Like, I'll just basically make it where when I send the program to the chip, I build a big file with all zeros, and then I load my code in at the top of that little file right there, and I send the whole block of essentially initialized memory plus my code. And so that's what I do here. I kind of initialize this block loader bytes, of data. I load my code into the beginning of that where it would live in memory, and then I send the whole thing. And so then it's easy enough to get the code there. Let's see if I missed anything on that. No, I think that's it. So the day of the attack, this is what it looked like, which is like, do not breathe on this wrong. Definitely do not let the dog in. Nobody should walk near these wires. Even you see how the Pico EMP is kind of sitting above there. If the temperature in the room changed from evening to morning, like everything would probably flex a tiny bit, and I would have to readjust to get this attack to work. So this is it working. This is what a real attack looks like. It's like you're just in the middle of it and you get it to work. So if your stuff looks like this, if it looks like a freaking hot mess, you're on the right path. Like, this is just what real kind of hacking looks like. The pictures, the YouTube videos, all that stuff, that's us cleaning it up after the fact, to try to make it like where we can actually explain what the hell's going on. Because the reality is it looks like this. Now, I did make a clean version for you so that I can kind of explain what it is, so that if you want to replicate this attack, you can do it. So I'll spend a little time here and explain it. So the devices we have in the picture, on the far left, that board with the two little gold connectors is a chip whisperer. It's kind of the conductor of this thing. It's orchestrating the entire attack. Now, what is going to the chip whisperer from the main processor is the reset line, because I need to reset this board kind of between each attack. The clock line, so I can monitor it to see like how's the attack doing from that kind of image I showed before. And then down to the bottom, a couple of triggers are going over to our Arduino board. So the first part of this attack is to use that Arduino board. So it's to reset the main processor in the middle, then use the Arduino board to send our first message. We send our first message, and then the chip whisperer tells the Pico EMP up top that I'm holding to send the pulse. Okay, and so we're in a loop and we're trying to send pulses at different places. We send the pulse, we then send another control line over to the Arduino to send the second message, which is the kind of the address and memory we want to load it and how much data we're going to send it. If we get a response from that message, so the way we get the response is that little CAN bus USB thing in the bottom right that's going over to our computer, our little TRS 100. If the computer sees that response to that message, then over that same CAN bus line, it sends all the code into our place that we want to run, our bootloader kind of firmware extraction code. Now, there's a couple other devices. The one that's right above where it says clock is another CAN bus decoder. So what I'm doing is, when I send the first message from the Arduino to the processor, I watch that message go across the wire and I feed that back to the chip whisperer. That's how it's getting its timing. That's how it knows when to send it. So it's actually seeing the message go across the wire. It's starting its timer. Timer gets to a certain point, sends the electromagnetic pulse. Then the Arduino sends the next message. I also have a little relay that's labeled power right above that. That's if like something goes completely sideways with the test setup. Like, so if that clock line just falls low and dies, I know I need to power cycle the board. Now, I don't power cycle the board every time, because time is like your greatest enemy in these kinds of things. If maybe you have to do hundreds or thousands of glitches before you get a successful one. So you're always trying to shrink the amount of time between glitches to the millisecond level if possible, so that you can do a lot of glitches and not take a lot of time. So I only power cycle the board when I know I'm in a state I need to power cycle it. Otherwise, I just reset it. You have the Pico EMP also has a USB line to the computer, and the chip whisperer has a USB line to the computer. Those are kind of controlling all the other functions there, like on the Pico EMP to adjust the voltage and everything like that. And so that's the kind of the whole attack in a nutshell. And when it works, you get a happy customer. Happy customer gets their code, and they're off and running doing whatever they want to do with that code. Now, a little bit on the data itself. So the data, when I get it to come out over the CAN bus, so if you run this attack, if you look at the code, what I do is I just use different arbitration IDs on the CAN bus to specify what data is being sent. So I send CAN messages at 100, and 100 is dumping the boot access module code itself. So to maybe try reverse engineering that and saying like, hey, can we find some other vulnerability? When I get to the end of that code space, I send a 101 as the arbitration ID. And so this little Python, script just sees 101 and it goes, okay, I'm all done with that. It writes the data, and then it exits out of that. It goes to the next part. The next part is waiting for 200 messages. That's the shadow area, the flash where the password of the board is contained. And then when it's done, a 201, and then the same for the main flash. So the entire flash of the chip comes out as 300. When it's all done, you get a 301. Now, one thing I should say about extracting the flash is that my code, the code you'll see on GitHub, doesn't handle the case where the flash is corrupted. So if some part of your flash memory is corrupted and there's a read failure, I basically just crap out, like the thing just crashes. Luckily, on the board that I needed to extract the flash from, there were no flash errors. So it extracted no problem. On the board I bought off of eBay, there was a flash error, which is probably why it was on eBay for 25 bucks. So I just kind of incremented past the memory and then continued and made sure my code worked. That would be an opportunity for improvement in that code. I didn't know how to handle that case, and I figured why even work on it if it works to dump the code. That's my only goal, and so it did. The cool thing is, now that this code exists, you could just buy some $25 board off of eBay. You don't need the Russian homie hookup to get the password because you have the bootloader. You could just build the glitch setup. You could glitch it once, get it to extract its password here, and then you would have a development board. But I didn't have this code beforehand, so I had to go the other route. Now, like I said, it's called MPC 5566 tools. It includes the one-shot stuff for the Arduino. It includes all the boot access mode applications, boot access module applications. So all the different iterations that I went through are all there. I even include what I call FlexCAN dumper, which was the final binary file that I loaded that worked. So if you can't get the stuff to compile or whatever, that's the one I load that outputs it in that format that I talked about. And then my entire Jupyter notebook, and Jupyter is what is used, it's kind of like a big Python notebook to control the chip whisper and everything else. So that's all there. So just a 5-day project, one of the comments. So this actually took like 65 days, all said and done. And I'm talking every day, like just weekends, everything. All I was doing was this. You can see the window, if you look at my YouTube channel, of like no publishing for an incredibly long period of time. That's this project. I just literally, I could not get my brain to do anything except obsess over this. So it's costly to take on a project like that because it has lots of other impacts, even if the money was all right. There's a question, how high is the chance you would corrupt your flash with the glitching? I didn't see any corrupted flash with it, but on some voltage glitching specifically to the 0-day attack you see that I did on the SAM4C32, which is on my YouTube channel, that one I was able to voltage glitch it and corrupt flash with like a long enough voltage glitch at the right point. So it's not without danger when you do this, but out of all the thousands and thousands of whatever that I didn't see any corruption of flash. But yeah, it's not without danger for sure. Like, you really got to be kind of planning these things out. Now, the interesting thing is the SAM4C32 only took me 2 days to figure out. So you contrast this, which is on my channel, with the 65 days of the MPC 5566, this thing, I already knew I needed to design a custom board. I already knew I needed to like control everything. And literally from the start of trying to attack this thing to getting an attack that let me pass the lock mechanism where I could extract the flash and get JTAG access on that chip was 2 days. And so that 2 days was possible because of the 65 days of suffering, basically, because I knew all the things. I had extreme confidence in my ability to do it. And the video that came out prior to this, I had so much confidence. I actually just said in that video, like, I'm going to extract the memory from this chip. Like, it was a foregone conclusion in my mind that I would figure this out after the struggle of the last thing. And I had my boy up there with the motivational messages in case I didn't get it done. Now, this will conclude it. There's some, I like reading books about art, I would say, and somehow the struggle of creating art and the struggle of reverse engineering, it feels like there's a lot of parallels to me. And so I saw this quote, which was, it basically starts that, creating art precipitates self-doubt. But to me, it's like reverse engineering for me. I mean, it's like I question everything about my life when I work on this, stirring deep waters that lay between what you know you should be and what you fear you might be. And yeah, that just really hits home for me. So I'll take a look at the questions. I'll see if there's anything there that you got that I didn't cover. If you have any other kind of questions, feel free to hit me with them, and I'll answer them, and I'll hang around a bit. Otherwise, this is the end. And thanks for joining and commenting while I was doing it.